Yes, hello. Welcome. My name is Valentin Shiravi. I'm a PhD student. I work at MIT and CSAIL in the Julia lab, and I work generally speaking on all things touching GPU computing, distributed computing, and HPC related things. As part of that, last year I spent a little bit of time and started writing like UCX.jl, which are language bindings for UCX, and trying to make sure that the UCX concepts and the Julia concept mesh well together, and you have a nice coherent experience. Well, so why Julia? Well, from a user's perspective, Julia looks a lot like it is a high-level dynamic language similar to Python, MATLAB, where it's relatively easy to write your numerical or system or simulations code. And so we've seen a lot of uptake in areas like finite element methods, fluid dynamics simulations. So there's Climber, which is like a big climate science project. And now we're also working with some other DOE projects and integrating Julia as one of the languages that they can both write their linear algebra routines in, but also which they might use as the user interface. And that is the difference between Python and Julia, is that you can write efficient code that is efficiently executed on the CPU or GPU, and get good performance while staying in the same language. So you don't have this more than one language problem that you often encounter in Python projects, where you have the user interface written in Python, and then you have the performant parts of the project written in C or C++. So I won't talk much more about all of this. There are some talks from me and other collaborators about this, and even some papers that we published. If you're interested, I'm always happy to chat about Julia use cases and how to, as an example, get GPUs working with Julia. If we look at like the parallelism model available in Julia, you have something that looks very similar to other languages. You have a distributed message-driven layer. Then you have some form of multi-threading. We have an explicit task-based system, so you don't reason about threads, you reason about tasks. Those tasks will be executed over multiple OS threads, similar like Go or async IO in Python. And then you have a lower level SIMD layer, which can be GPU accelerators or SIMD units, depending on what kind of architecture you're targeting. So for the distributed part, in Julia, you have two choices, and this is what makes things a little bit difficult sometimes. So you have MPI.gl, which is rock solid, very well supported, and most often the project of choice, because it scales up, and especially for algorithms that have excellent weak scaling, like MPI is a known good choice. And for other users, they might find MPI a little bit too, not complex, but it requires a shift in perspective. It's not like you're running one Julia program and you're connecting to different workers, and you have one primary Julia program executing. That shift from like a single sequential process to MPI processes is something that you need to teach users. And so some people prefer distribute.gl, which is a remote procedure call based implementation. So we will go from one worker to the other worker, and we will call a function on that worker. And so you have a primary worker model. So you have one primary process, and it is kind of acting as the conductor to tell all of the workers what they need to do. And based on that, we have something called Dagger.gl, which is similar to Dask, which allows you to write a program and then have it automatically be distributed across all of these workers. Then on the layer beneath, you have task-based parallelism. And so we have these macros at sync and at spawn, which will at spawn will create a task and will then execute that task on potentially a different thread. and at sync will then synchronize a set of spawns within a region. And one of the projects I've been working on over the last few years the most is the GPU support in Julia. And one of the differences is that we are really trying to get Julia all the way down. So we're using LLVM to compile code from Julia directly to the assembly language of the respective GPU. So NVPTX or ROCm's variant thereof. And so you have vendor-specific packages, some of the CUDA.jl, AMD GPU.jl, OneAPI.jl, which implement low-level interfaces to these different accelerators. And they're backed by and built upon a common infrastructure where we're sharing all of the nitty-gritty details of how do I compile Julia to various accelerators. And so bringing up a new accelerator is actually a lot faster than bringing up the first one. So UCX.jl. It features an auto-generated wrapper using Clang.jl. Right now it's based on 1.10. And the APIs I've wrapped so far are UCS and UCP. It has high-level support for active messages, and then tag send, tag receive, stream send, stream receive. And it has integration with Julia's event loop, which is what the primary part of this talk is going to be about. What I'm working on, hopefully soon when I find some time, is adding support for RMA and updating all of the bindings, the web generated to 1.11. So a quick example of how this all looks like if you're using the UCX interface is there is this endpoint, which is wrapping a UCX endpoint underneath. And I can implement an echo server straightforwardly, taking the example from the UCX repository. And so I wait on somebody to connect to me, then I spawn this echo server function, which is a Julia function, and I wait for a message being told, well, how large will the data actually be? Then I can allocate the buffer in which I will receive the data, wait on the data to be received, and then send it back across the endpoint. And so the client looks very similar. Instead of the 2 receives, it will have the 2 sends. Then it will wait for those sends to finish, and then will do a wait, sending the receive thereafter, since it knows itself how large the data will be. You notice that all of these are waits, which means, right, by default, everything is non-blocking. So if I post a receive, I will get a token back, and I can wait on a later time point to make sure that that send has actually finished. The client itself is fairly straightforward. I just start a UCX context, I associate a worker with it, I create an endpoint connecting to an IP address and a port, and then I run my client function over the endpoint, and when I'm done, I will close my worker. On the server side, it's a little bit more complicated. I have the same UCX context and UCX worker, but then I need to create a UCX listener with a specific callback. And so this callback is, again, a Julia function. And when it receives a connection request, it will create a Julia task with some little bit of magic to make sure that we will print error messages well. And then stored the echo server function with the endpoint constructed from the worker and the connection request. This little loop down here makes sure that basically we ensure that the connection will be made. So when I run this locally, as an example, I have here my server. I start it up. It's now waiting for connections, and then I can start my client, and it will connect to the worker, the server. The echo server is being started. I'm getting the data, sending it back, and I'm exiting. And so this is a variant of the code I showed you, just with some debug statement to show what's actually happening. The big challenge that I encountered with UCX.jl was, besides like getting everything wrapped up and wrapping my head around all of the UCX terminology, was mostly with integrating with Julia's event loop. So Julia uses libuv, which comes from the JavaScript world, and that has an event loop. And we need to now integrate that event loop with the UCX progress model. So ideally, we want to use all of the non-blocking variants of defined in UCX. And while we're waiting for the requests to happen, to finish, etc., we would love to execute other Julia code asynchronously. We also need to guarantee that progress is being made. So one of the things, like in UCX, you always callbacks only happen when the UCX progress function is being called on the worker. So you need to guarantee that that happens eventually, otherwise you will not receive your callbacks. And of course, there are other points. I think if you're calling into the API to do another send, you might also call progress in the progress of doing so, pun intended. But generally speaking, we need to guarantee that progress is being made. Another wrinkle is that callbacks from UCX will execute normal Julia code with all of the things Julia code can normally do. And the biggest challenge was to actually get reasonable active messages latency, because different ways of doing this. And yeah, so the approach I came up with is this: while the worker is open, wait on the worker. And so we are using three different mechanisms, and you can choose which one. Either to ensure that, akin to a background thread, but not running separately, but within the Julia event loop, that progress will be made on this worker as long as this while is open worker loop runs. So the three progress modes are: first, polling, that has the highest latency, and I will talk about why in a little bit, but it has also the lowest resource utilization. Initially, I implemented a busy loop, which has very low latency, but has problems with scheduling in the Julia world. And then I tried a third approach, which uses libuv's idling infrastructure, which has low latency, but has unfair scheduling on the OS level. And so you can kind of choose your poison. I haven't found the perfect balance yet. And so I would be interested in different approaches that people have come up with. And so this is this while is open loop I was talking about. So you can spawn off a different Julia task, and while the worker is open, you wait on the worker, and this wait call guarantees that progress is being made, and we will call the progress function repeatedly. So polling uses the UCP facility to get a file descriptor and then wait on the file descriptor for notifications. So it uses UCP worker get EFD and worker arm. Plus, then the Julia side uses filewatching.gl's pollfd. And so you can wait for notifications on this file descriptor. That requires interaction with the kernel, and so that's why the latency is quite high. Additionally, that requires the UCP feature wake up, which, as far as I understand, currently will disable shared memory support. And so you will get higher latency cost again, just because you're using shared memory, because you can't communicate through shared memory. The other mode is idling, which sounds, when I first read it, I was like, oh yeah, that sounds like the ideal thing. Every time per loop iteration, we have a callback, and we can call that callback. Every time the libuv event loop runs, we will run a callback, and that callback could just call progress, and therefore we would, every time it runs, we would make progress, and that's probably the best of what we can do. But the problem is that as soon as I register an UV idle handler, the loop switches from waiting for actual IO work to happen to just executing in a busy loop as much as possible. And so we kind of start hogging OS resources. And so there's why this warning is, despite the name, it is not actually waiting for the event loop to be idle. It will actually cause the event loop to run as often as possible. The other option is to implement it in Julia. This is the first approach I tried. It's a busy loop. But the problem is now we could see live logs in the Julia task system. So the Julia task system is cooperative. That means that it is required for task switching to happen, for fairness to happen in the scheduling, that the task will occasionally call yield. Now, it could happen by a freak accident that the scheduler decides to just always schedule the task executing the busy loop because there seems to be something happening, right? It is executing code and it is yielding back into the scheduler. So probably that is an important task. We should execute it all the time. But we're waiting for a different task to actually make progress because it is fulfilling a request or something else. And so you could see something like spurious pseudo-live logs where the system seems to be making progress, but actually because you're hogging the execution slice, progress is not being made as fast as you would like. I did some latency benchmarking on both PowerPC and x86, and polling by far has the highest latency cost. Both busy and idling have good performance in that regard. And then on PowerPC, everything is generally slower. And that's probably due to the fact that like Julia tasks are not optimized on PowerPC yet. Other alternatives I considered, like the default answer might have been, well, just start a non-Julia thread, execute the progress function on that non-Julia thread, and everything should be fine. Well, the problem is callbacks are indeed Julia functions. They will interact with the runtime. They will do garbage allocation. They will do task switching. I can't do that on a non-Julia thread. So alternatively, I can make all callbacks very lightweight and basically just trigger UVAC sync, which is a facility that allows me to enqueue work into the libuv event loop from outside. So we could have a multi-stage callback. While UCX invokes a callback, libuv notifies Julia that there is a callback. We will switch to the task notified. Haven't implemented this song and dance, but the problem is we will definitely have higher latency. We will definitely have more allocations. And the other issue is that we basically could never return a status from the callback to UCX proper. And that's, as an example, is needed in the active message receive callback. There is another wrinkle, which is for most callbacks, when I just implemented tag send, tag receive, and stream send and stream receive, they were fairly simple. They would just be executed. They would notify a Julia condition object that the task has now finished, set the status object, and then be done executing. So there was not much interaction with the Julia runtime. There's very little risk of actually switching inside that callback. But as soon as I added active messages, suddenly the code run in those callbacks became bigger and bigger. And one way around it is to actually, as part of the active message callback, to defer the execution of that callback to some later point by spawning a Julia task. But that adds additional latency. So, trade-offs. So scenarios I run into where the progress function would call an active message callback. That callback had, for debugging purposes, as an example, a print line statement in it, which will cause a task switch, which will cause Julia to switch to my busy loop, in which I'm calling progress. Progress will be called again, and at this point, UCX has the assumption that a given thread will not recursively call progress. Different threads can call progress simultaneously, and they will make progress on different items, but the same thread cannot. And so you could actually get an infinite recursion because it would pick up the active message handler currently being executed, try to invoke the AIM callback again, which might just doing the same thing, and you would get very weird side effects if it wasn't fully recursive, or you would just crash the system. So what is on my roadmap for the next couple of months if I find some time? Well, I need to go back and take a hard glance at whether or not UCX.jl, as it is implemented right now, works well with Julia threading. So Julia threading has been evolving over the last couple of years, and when I first started with UCX, it wasn't as powerful as it is right now. So in Julia 1.7, we added something called thread migration, a task migration, where we will migrate a task from one OS thread to another OS thread in order to do work balancing. I want to add GPU memory kind support, taking inspiration from MPI.jl, which is the fully featured MPI interface in Julia. And I think in 1.10, the attribute field memory type was added, or maybe in 11. I have a prototype of that working, but we can communicate to UCX because we have colored pointers. Well, what is the memory type of the data I'm passing to you? And make sure that the right actions are happening. As I mentioned in the beginning, we have this library called distributor.jl, and I have a prototype implementation of that using UCX, but it's rather complex to emulate all of the protocols there. And so it's not sure whether or not doing a full-fledged distributor.jl implementation over UCX.jl makes sense. But we have a lot of libraries that do data movements, and they need to do GPU-aware data movements. And so we can use UCX, or the plan is to use UCX as part of those libraries. So before I end my talk and open it up for questions, one of the gripes I have about UCX, as an example, is how it deals with signal handlers. It assumes that any kind of signal handler is basically bad, and installs its own signal handlers by default that will abort the program when it sees one. That's annoying enough because OpenMPI did this, or other MPI implementations do that as well. But in Julia, we use signal handlers all the time to implement things like garbage collection or multi-threading or profiling, etc. So we have to disable this, and we have to disable this actually because of UCX all the way up at the MPI.jl level. And so you can go to this URL, and there's like known issues that we found when trying to use OpenMPI and Julia. On the UCX.jl side, the first thing I do is I actually disable the signal handlers after loading the library. There are other things like UCX is intercepting the DLOpen functionality in order to to intercept CUDA's memory allocation routines in order to figure out and cache the color of a pointer. Is this a GPU pointer? If so, I need to do something different. And so it's working around the latency of the CUDA interface for actually querying the fact that this is a CUDA pointer. And this might be a good choice for C and C++, where like adding the knowledge, oh, by the way, this is a CUDA pointer from the user side, is very tedious because it's just a pointer. Right? You don't have a color to the pointer is not special. In high-level languages like Julia, and I think also Python, we do know when allocation came from CUDA. We had to deal with that especially to begin with. So we have more information. So this is the development towards having a memory type is actually great. The bigger challenge, of course, here is I can support it directly in UCX, but how do I tell OpenMPI that, by the way, this is a CUDA memory pointer? Generally speaking, I would love to be able to require explicit opt-in instead of opt-out for those invasive features and collaborate with the UCX core developers to make the interfaces richer so that we can provide the information instead of having a system library that we load and that replaces a different part of the system. If you have questions, I think we have about 4 minutes for questions. If you want to talk about Julia or Julia in HPC, we have a monthly call on the subject. It's on the 4th Tuesday of the month at 2 p.m. Eastern. It's open to anybody. It's on the Julia community calendar. And you are also very happy to contact me directly, either by email or on the Julia Slack about this talk or other collaborative efforts. Thank you.
Yes, I actually have a few questions about mainly the issues that you presented in the slides. First, the issue related to the event loops. So I think that actually the UCX callbacks, or more precisely the callbacks that you pass to UCX, they are supposed to be pretty lightweight,
Yes.
mostly like adding something to some list or marking some variable as completed. So from that perspective, maybe what you suggested as the last approach, to add some external event to the event loop, would actually be the best approach. Because the
Yeah,
UTX,
I think so as well. The question is how much additional latency will that add? But I probably should just go spend a day and at some point implement it measure.
so to put it in the context, the UCX callbacks are called right from the context where we pull the message from the hardware. So if there was some maybe an alternative approach where you maybe receive data from some socket or from some other kind of queue, you don't have this queue at all in case of UCX callback. So might as well just add it in the Julia layer. It should not add additional latency compared to, let's say, a reference implementation where we have this queue already in the network layer.
Yeah, it's more that it will require another loop iteration of the event loop before that event will then processed. So we will process a callback in Julia. We will then do all the work and then get back to libuv, which will tell us, oh, by the way, since the last time we got around, these are all of the callbacks that got executed. And so that's the latency I'm worried about more. And the other aspect was, well, I can probably just do active messages completely asynchronous. That's what I do for most of them right now.
Yeah, so for active messages, you could also return a UCS in progress from the active message
Yes.
callback, which means that you just take ownership of the data and pass it to the second stage.
Yeah. So right now I do that depending on the size of the data. So it's up to the active message callback implementer, so the user of UCX.jl to make that decision. But in the prototypes I had, I was making that decision on like a threshold for small or big data.
Yeah, that makes sense. And the next I wanted to ask is about the GPU memory support. So the hint that you have in the API to pass memory type, just to make sure it's not really mandatory. If you don't pass it, UCX would try to query the pointer or look up in the cache. If you already have it somewhere, then probably it would be more efficient to actually pass it. And do you see any issues with the DL open hooks that's causing problems with Julia, or just?
So I think that was my first interactions with like UCX 4 years ago, when we got reports that using OpenMPI would suddenly crash Julia in weird ways, and it took us quite a bit of energy and effort to debug the DL Open to get to the point where we realized that the DL Open implementation at that time was broken. And mostly that was about RPath handling. And UCX since then fixed that. But I still to this day, like if you go, I can put the link in the chat again, or we can quickly go to it. We like MPI.gl disables the memtype cache by default.
Is it because you saw problems with detecting pointers or problems with?
I think this is the last open issue. I haven't had time to debug that at some point deeply, but yeah, we turning the memtype hash off at least worked around that.
So yeah, I think maybe we should, if you could give a try to latest UCX versions. We had some fixes in this area, especially around the CUDA memory hooks and related to a memory type cache and static link of CUDA. Maybe it's no longer mandatory.
Yeah.
And another thing I wanted to ask, if the event loop is only based on polling, or do you have anything which is based on file descriptors and things like epoll or select?
So the polling one is, so my polling implementation is based on the file descriptor.
So are you using a UCP worker file descriptor for that?
Yes.
Okay.
I think you mentioned that like shared memory did not work, and like I chatted with Yossi offline, and shared memory is supposed to work with file descriptors.
Okay, so then
it has been introduced a while ago, but if you go with latest version, for sure.
Okay, then maybe the issue is just still open, and we need to close it. That would be fantastic. I think Python had the same run into a similar issue. Okay, but my time is over. So,
any more questions for Valentin? We have a little bit buffer, so it's fine.